Now what we have here is, as you can tell, this M1 will be sliding down and M2, these wedges will be moving on the horizontal surface. So if I'll say this both the wedge will be moving in the horizontal direction with equal acceleration but in opposite direction, is it okay for you to get that? Why? What I'm telling is, maybe I'll draw that even. So if you will draw the free body diagram of both the wedges, just a moment. And also the rod. So all of you have tried this question, no? Now the force that will be acting on the wedge by the rod, we understand that it is going to be the normal contact force, correct? And to draw the normal contact force, we must draw the common normal first, correct? And then along the common normal, the normal force will act in a manner such that it will try to push the objects away from each other, no? So the normal contact force, the one that is going to be acting on our wedge will be, suppose N. Same normal contact force will be acting on our rod, correct? And then for the rod to be able to move down while maintaining contact with both the wedges, for that reason these two wedges must be moving in the opposite direction with equal velocity, that we understand, no? And equal acceleration even. If at all it is not like that, then the rod can't remain in between them and can't move down while maintaining contact with both of them. And you will see that once we will solve further. And also, since these two wedges will be moving in the opposite direction, suppose if I'll assume the wedge are moving with an acceleration a2, so this one will be also moving with a2, because the forces that will be acting on it is going to be same, not same, I can say similar, you can tell. So the normal contact force, the one that is acting on our wedges, I'm going to draw that. Just a second. So as it is given, this angle is theta, so the angle made by the normal contact force with the horizontal here, can you tell me that, everyone? So don't draw triangles to tell me that angle. What I told you, the angle between horizontal and the inclined is theta. So the angle between the one that is perpendicular to the incline, correct, and the one that is horizontal will be 90 minus theta, no? This angle, all of you can tell, it's going to be 90 minus theta. Anyone having any trouble with that? Angle between two lines theta, so angle between one of their perpendicular and one of their parallel will be 90 minus theta. They did not get it. The angle between horizontal and the inclined plane, you can find that angle on your own also, you should be able to, but I'm telling you some alternate way. Angle between horizontal and the incline is theta, so angle between their perpendicular will be theta, angle between their parallel will be theta, and the angle between one of their parallel and one of their perpendicular will be 90 minus theta. So what we have, angle between the inclined plane and horizontal is theta, so this common normal direction perpendicular to the inclined plane, this horizontal parallel to the horizontal here, so angle between these two must be 90 minus theta. And you check that thing by the other ways that you do, that alternate opposite angle, this theta, so this will be 90 minus theta. That is something simple, but you should be having the habit of this one also. So this angle theta, so you can tell this angle will be theta only, so this will become 90 minus theta. But I don't want you to come to this conclusion via that way. So if I'll take components, what we have is n sine theta will be acting on our wedge this way, and n cos theta will be acting downward. Same goes here also. the component of the normal contact force along horizontal direction will be n sine theta, and one will be n cos theta downwards. No, all of you are getting the free body diagram? No issue with that? Those who have joined late, do you want me to explain this thing? So one thing, okay, I'll tell you. See, what we have is, first we'll have to assume in what way they must move, no? And you can tell this rod will be coming down, and for this rod to be able to be in contact with the surfaces of both these two identical surface wedges, it must be this wedge left one and the right one must be moving in opposite direction with equal velocity and equal acceleration, that you can tell. Otherwise, it can't be able to maintain contact with both of them at the same time, isn't it? So the amount by which this M2 must slide towards left, by same amount, this M2, the right one, must slide towards right. Correct? So because of that, I can tell that these two wedges must move equally in opposite direction in same time. So they must be having equal velocity and equal acceleration. Just they are going to be acting in opposite direction. So I assumed that our wedge is moving, this wedge left one moving leftward with A2, right one moving rightward with A2. Then we are indicating or drawing the forces acting on it. So the force that will be acting on our wedge will be, one of the force will be the normal contact force, and that will be acting along common normal. And how it will act? It will act in a manner such that it will try to push the surfaces away from each other. Correct? Normal contact force, maybe I'll draw some bigger arrow for that. Just a moment. So this is the way the normal contact force will be acting on our wedge. So, and then this angle 90 minus theta, so its component in leftward direction and sine theta downward and cos theta. There will be one more normal contact force acting on this wedge from the ground and dash. No use here, but still I'm drawing it. You must have habit of drawing all the forces. M2G acting downward. So what you see is that if I will write down, so same exactly will happen for this guy as well, and dash and M2G, no? Yes, tell me. Yes, so n cos 90 minus theta is n sin theta, no? Okay, no? So you will find the net force acting on either of the wedges is n sin theta, as I am drawing here. You can see that. So the only force that acts on the wedge in their horizontal direction is n sin theta. So what we'll do, just I'll write down F equals to ma. So what we have is n sin theta is going to be equal to m2a2. This is our one equation that we can make. Next, to draw the forces acting on the wedge, you don't have to do much hard work. I told you, that if you know there's a force which is acting in action-reaction pair, so even their components will be in action-reaction pair, no? Isn't it not? Indian parents hating Pakistani parents, so their children also hating each other, like that you can think of. Or that just I'm making some point. So the component of, so what we have is, as you can see, the normal contact force, the one that is acting on the wedge in the horizontal direction, the component of the normal contact force is n sin theta. Or we can say the rod is pushing the wedge in the horizontal direction this way by n sin theta. So our rod will be also pushed by same or not. I've drawn too closely. Maybe I'll draw for the rod separately. All of you are getting that point. You can still find the angles and you can still take the components, but I am asking you to avoid any kind of extra hard work. So you see how the force is acting on our left wedge by the rod is n sin theta this way and n cos theta down. So exactly opposite forces will be applied on our wedge, on our rod. So it will be n sin theta this way, n cos theta upward. And again from this side we are going to have n sin theta this way and n cos theta upward. So what you find is that the net force acting on this rod in the horizontal direction 0. No? Maybe I'll draw some nice looking figure, just a moment. the normal contact force, the one that is acting on the rod, is like this. Its components are going to be n sine theta, n sine n sorry, n cos theta upward, and again from this side n sine theta along horizontal and n cos theta upward. So what you find is that for this rod, net force along the horizontal direction is going to be 0 now. And we have got one more force acting, that is our gravity m1g. And what I'll do is I'll assume that this rod is going to be falling down with a1. So I'll write down the net force that is going to be acting on this rod in the downward direction, taking downward as positive. So what we have, the net force in the downward direction is going to be our, so see, you see that n cos theta here, n cos theta here, 2 n cos theta acting upward, and we have got m1g acting down. So downward I took positive, so m1g minus of 2 n cos theta is the net force acting in the downward direction. So what I write down, the net force in that direction must be equal to the mass times acceleration. So that is going to be m1 a1. So this is how we have got equation number 1 and now equation number 2. And now you will see, still we are not having enough equations to solve for the given unknowns. We don't know a2, we don't know n, and we don't know a1. So 3 unknowns, but we've got 2 equations only formed. So we will use the rigid body constraint to find the constraint equation here, and that will come exactly same as the one that we have got for the earlier question that we did in the class. So I copy this thing. Anyone having doubt, you ask me. And while you copy those who have joined after some time, if you did not understood, you ask me, I'll explain this thing. All of you got it now? Copy. After copying, tell me. Aswin got it now? Yeah, I also didn't want to take extra class, but what to do? I also wanted to enjoy my holidays, but I can't compromise on the content by finishing the syllabus just to finish the syllabus. So you understand that why I have to take the extra class. And phase 5, we don't get any time at all. This is how I'll get extra time so as to finish things properly. Varun got it now? Mageshwar got it now? Okay then. Sound quality better no than last time. Okay then. Now next, what I told you to draw the rigid body constraint. First you draw the bodies a little bit separated from each other. Okay no. And then you draw the common normal, indicate the velocities that they have got. So it is supposed to be maintaining contact. Please tell me. No problem. Copy. Take your time. You are at home only, so it's not a problem. We have time. Just tell me. Yeah, I am recording also. Yeah, I am recording it also. But I have to share it. Actually, I am doing the screen recording. No, it becomes 8 GB, 10 GB. So I have to little bit crop it and then I have to send it. So there's no guarantee that it will get recorded. I don't know. Sometime it space gets over. So that's why don't rely on that. But I'll try to share that thing. Okay. Okay. So I saw one other thing. Maybe there's something called. Okay then. So maybe if after 1 week, if still we be taking some extra classes like this, I'll buy some better one where I'll have things getting recorded directly. Just a moment. So what do you do to draw the free body, to figure out the constant equations? First you draw the surfaces, the one for which you are writing down the rigid body equation, that constant equation, a little bit separated from each other. Draw the common normal and then indicate their velocities. So the wedge is moving with the velocity, suppose v1, v2, no, v2 in this way, and our rod is falling down with suppose v1 at any point of time. So this angle theta, so what you see, this angle is also going to be theta, no? So the component of our v2 along common normal, so what is that? That is going to be v2 sine theta, no? And what is that? That is the velocity of the point, the one that is on the surface of the wedge but in contact with the rod, correct? And now you check it out. The angle between horizontal, see sometime making triangles may become difficult. Here easy, maybe in some other chapters it might be. We don't know. So if I have this horizontal and this incline making angle theta, so see this common normal is going to be perpendicular to the incline, and this v1 is in the vertical direction which is perpendicular to the horizontal. So between them angle will be same. So this angle should be also theta. So the component of our v1 along common normal is v1 cos theta. Now you think like that, as if I have a particle which is going with a velocity v2 sine theta, and it is being chased by another particle which is moving towards it with v1 cos theta. And for them not to have any change in the separation, their velocities must be equal or not. So that is what I will do here. So we'll have v2 sine theta to be equal to v1 cos theta. So v1 equals to v2 tan theta. Now whenever you are going to differentiate any kind of thing that you get like looking like this, you must make sure if in there every term is constant or variable. So v1 not a constant, v2 not a constant, but theta here constant, no? But it may not be, we don't know. So you must be careful in there. See that whether that angle is changing or not. So here theta is constant, so differentiating is not an issue. Differentiating v1 will give us a1. Tan theta constant will come out. Maybe I'll do that differentiation also. Just tell me. Yeah, that's what. No, they head towards same direction. Then only they will not have any. They are not going to have any change in separation. No? Suppose if they are heading in, one is going with 5, another going with 5 only, but opposite. So separation will change. No, when I can have separation not changing, when they are going in the same direction with equal magnitude also, no? Correct? Right. So always think like that, then it will become very simple. So differentiating b1 will give us a1, then tan theta will come out. Differentiating v2 will give us a2, so it will become a2 tan theta. So this is the equation number 3. So now 3 equations you have got. Now it is your problem to solve and find the unknowns. Not a problem, that is something you should be good in that. That is not physics. So that is the problem. Even if you know physics, sometimes you don't get the answer because of you're not good in calculations kind of thing. So you must become good in that also. So I hope all of you understood this thing. Easy question only. More we will do. Okay, some difficult questions also we will do. But that I will do in offline class, so that you may understand it in more better way. So copy this thing, all of you. After copying, tell me. I found one app, Blue Jean Cities. Okay, so that is platform which I found. Yeah. That one not good, man. That one I tried, so not good. Mm. I was unable to unmute my. What happened in there? From iPad, I can't make the sound to become zero, and I have to use two devices, one for camera and all. That's why it was not working there properly. Other one I got a little bit costly, but maybe I'll try that. So uh, I'll share that link to app or whatever it is. Okay. It is supported in all platforms, so that is not an issue. Their recording I can do without much headache. That's why, just for recording purpose only. Because after class and all, I don't get that kind of time that I can edit and share it. It becomes too much headache. Okay, I can take a new page now. Okay. Next, we'll try that other question. We'll solve that other question. So there is a question that I gave you. There's a reason for giving every question. What is given here is, just I'll explain once. This two wedge is given that they are moving with velocity v1 and v2 at any point of time, and also they have told us in what direction we are supposed to have our y and x direction to be taken, and we have to determine the velocity of the sphere in terms of v1 and v2 so that it remains in contact with both the wedges. Okay, so now one thing you must take it like a fact also, or like a standard practice, I can say, that whenever you have to find a vector, so in maths you might be doing those things from a long time, no? Something unknown, you will assume it x, and then some story will be given and you will make equation out of the story, and then you will solve for x, no? The same kind of thing we will do here also, but here what I have is unknown is the velocity of the sphere. So not knowing a vector is like not knowing two things. Means you don't know the direction of that vector, you don't know the magnitude or length of the vector. So it means we'll have to assume two things, one is length and one direction. But assuming direction, little bit headache, no? Like from what direction, what angle and all, it becomes confusing sometimes. So that's why better way always is, or most of the time I can say is, to assume the vector in terms of the components. Because if I'll give you a vector with in terms of the components it has got along xyz, everything can be found about that vector, no? So first, so what I will do, I'll assume the sphere, velocity of the sphere, by assuming it in terms of the components. But whenever you are into assuming a vector in terms of the component, you must first look for what all components are possible for the given vector. Okay, now. So what all components are possible for a given vector? So what I mean by that, it's suppose if I'll have this sphere moving, it must be having its velocity in the plane of the screen only, no? Or it is going to have just x and y components only. So it means this vector has got only two components. It means two things we don't know. It means two unknowns. Two unknowns means what? Two unknowns means for us is we have to form at least two equations. And from the question itself, you can look and tell it is supposed to be making contact with two surfaces at the same time, simultaneously. And because of that, we can frame one equation for, we can make one equation out of each surface. So we can make two equations also. I hope you understood that point, no? So maybe I'll write that thing even. Always try to assume a vector in terms of its components. And here the velocity of the sphere can have two components only. So what I will do, I'll assume the sphere has got a velocity along x and y, or suppose the velocity, or I'll assume that velocity of the sphere is going to be Vx I cap plus Vy j cap. So what we have got two unknowns, that is Vx and Vy. So we'll have to form two equations to solve it. No? And two equations will come from the two surfaces with which it is supposed to be making contact. So it is basically a question of checking that whether you know that rigid body constraint or not. So what I told you, whichever surfaces for which you have to write that, you draw those two surfaces a little bit separated from each other, isn't it? So first, maybe I'll name this spheres and this wedges. Suppose this is A and this is B. For the sphere to have contact with A always, I'll draw the, we'll figure out the rigid body constraint for that. And suppose this is the surface of our wedge A and sphere. So first you draw those two surfaces a little bit separated from each other, and then you draw the common normal, and any normal drawn to a sphere will be passing through its center or not. It is like a circle kind of thing. That is 9th and class math, no? No use here, but you must know that in drawing free body diagram it will come in handy. So what we are told is that our wedge A is moving with V1 in the leftward direction, correct? So if I have a rigid body, maybe this pen, doing translational motion, means not rotating, just moving. In that case, every point is going to have same velocity, even the point of the wedge, the one that is making contact with the sphere. So the point on the wedge, the one that is making which is in contact with the sphere, will be moving with V1 in this manner. And the point on the sphere, the one that is in contact with the wedge, is going to be moving with the velocity of the sphere, that is Vx in the x direction we have assumed, and Vy in the y direction. And after that, it is very simple thing that everyone must have got it, that you find their velocities that is there along the common normal direction, isn't it? So this is our common normal. Now, after this, it is all about finding out angles and all, nothing else. So if this angle given to as 53 degrees, so find this angle, and this angle, everyone fast, as fast you can. What you will use? The angle between two lines, then perpendiculars, parallels, one of their perpendicular, one of their parallel. Yeah. So this angle, so check your answer. This is horizontal, this is inclined plane. Angle between them 53 degrees. So angle between the one that is perpendicular to the inclined plane, this common normal direction, and one parallel to the horizontal, this V1 direction, will be having an angle 90 minus theta, so it must be 37 degrees, correct? Now next, angle between, this is common normal, and this Vy is in vertical direction. So angle between the one that is perpendicular to the inclined plane and the one that is perpendicular to the horizontal, which is vertical, along which we have got Vy acting, will be having same angle. So this 53 degrees. So automatically the other one will be 37, that you can tell because angle between Vx and Vy is 90. Then you take component of V1 along common normal, that is V1 cos 37. And to get the component of the velocity of the sphere along common normal, you can find the component of their component also, is it not? So component of Vx along common normal is going to be our Vx cos 37. And the component of our Vy along common normal will be Vy cos 53. So it is like one point that is running away with V1 cos 37. It is in this moment. And the other one point is moving, changing this point with velocity Vx cos 37 plus Vy cos 37. Cos 53, sorry. Correct, no? Getting the point here. So for them not to have any change in the separation, V1 cos 37 should be equal to Vx cos 37 plus Vy cos 53. And then we know cos 37 is 4 by 5. So 4V1 by 5. 4Vx by 5. Cos 53 is, just a moment, just a second. And cos 53 is 3 by 5, so it will become 3Vy by 5. Simplifying it, you will get 4V1 equals to 4Vx plus 3Vy. That is our one equation from one surface. Next other equation we will get from other surface also, like that. That is easy only. So can you do that, finding that other equation on your own? That is very easy. Just the moment you draw the diagram, automatically you can see that on your own. Do that thing. I'll give you like 30 seconds. More than that not required. How answer 1? This is equation number 1, dude. How answer 1? And what you mean by equation has answer 1? I don't get that. I don't know that language. What is the meaning of equation having answer 1? Unknowns will be equal to something. How equations will be equal to anything? 9th, 10th class you have gone online, no? That is the reason. I think so. Okay, for the other surface also I'll draw here only. Just a moment. Now for this is our sphere and this is our wedge B. Now what will be the common normal? Common normal will be nothing but the horizontal only, no? Is it not? This is going to be our common normal between them. And then you draw their velocities. So what we have is the wedge B, or the point on the wedge B, the one that is in contact with the sphere will be moving with V2, and the point on the sphere, the one making in contact with the wedge, is moving with Vx and Vy. So what we find is that the component of the velocity of the sphere along common normal is just Vx. Component of Vy will be 0 along horizontal. So what you have is the point on the sphere is running with Vx and it is being chased by the point on the wedge with V2. So Vx must be equal to V2. That will be our equation number 2. So easy or not? Two equations, two unknown. Okay, so we got it now? Correct now? So what we have is 4V1 equals to 4Vx. Vx is V2 only, plus 3Vy. So from this we will get Vy equals to 4V1 minus V2 by 3. And Vx we have got it as V2 only. So velocity of this sphere we know or not? It is Vx I cap, Vy j cap. Copy this thing everyone. I hope all of you understood this question. Yes, tell me. Yes, tell me no. Yes, yes. No, 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 no. V1 and V2 are equal, we can say, when they are in contact. And if V1 V2 is the velocity along common normal, no? What are equal? The velocity along common normal equal, no? Of whom? The one that are in contact. They are not in contact. Sphere, sphere and two are touching each other if wedges are in contact, and then if V1 V2 are their velocities along common normal. It's not just about their velocities, it's about their velocities along common normal, no? What is equal? Velocities along common normal. They are allowed to rub against each other. Relative motion while they are in contact is allowed. What is not allowed? For them not to get separated. Getting the point? So see, this way they can move. Totally okay. But they can't get separated. So for that to happen, their velocities along common normal must be equal, or the velocity of separation must be equal to 0. Correct? Now you got that, no? No confusion now? Yes. Okay. Copy. Next we will talk about friction force. So friction force, just like normal contact force, is also a kind of contact force. And we talked about what is the reason behind the contact force to come into picture, or basically Vx I cap, Vy j cap, that is what we assume the velocities. Okay, two unknowns we have, no? Vx, Vy we don't know. And so two equations we have to form, and we can form it since I have got two surfaces, and we will write the rigid body constraint for each surface, so we will get two equations. Good, no? Okay. So see, please tell me. Their velocities along common normal must be equal. That class you were present, no? No. No, 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 no. Yeah, yeah, yes, correct, correct. So that's what, no? Velocity is equal. So I differentiate that. So acceleration also becomes equal. But that I am not asking you to do that thing, because directly I can see, suppose if I had a case that theta was made to change somehow, maybe somehow, then I can't differentiate and equate it like that, no? Getting the point? I have to see how what will come as see if I at all v2 and tan theta both were functions of time, then we will apply product rule. No, we can't take tan theta outside just like this in case like when it is constant. Getting the point? That's why I'm not telling you that. There's a reason for anything I speak. Okay, accelerations not equal, because I know that somewhere they can do this kind of changes that theta are changing, then in there that statement will become wrong. Okay, understood? No? Okay. Copy after copying, tell me. For a student to be able to get good quality, but I don't think any good student will do anything like that. Okay then. So one thing we talked about, every force, what is the origin of that force is, no? Like a normal contact force, what was the origin? I told you nothing never touches. It is the electron repulsion which gives you the feel of touch, but nothing never touches. Correct? So, and that was the reason because of the electric forces. And I told you, whenever we talk about electric forces, we don't talk it about alone. We talk in pairs with the magnetic force also. Why? I can't tell you that now because no need to tell now. This is to be told in 12th class. So that's why we say those forces as electromagnetic. Same way, the origin of friction force is also electromagnetic. Okay. And the friction that we are going to talk about is sliding friction. The origin of this force is electromagnetic. And whatever we tell about friction, we tell by experimentation only, that how the friction force behaves. So suppose if friction force will act always in a manner to prevent the surfaces from slipping onto each other, or to prevent the surfaces to have any relative motion between them. Suppose if we'll do one thought experiment, or real experiment also you can do. It's not like some difficult experiment. Suppose if I'll take a block of mass m as a mass, and then I keep it on some rough surface, and then what I'm doing is I'm applying a force onto it in the horizontal direction, and what I find is this block doesn't move. Getting the point? Suppose you're going dark and somewhere your cloth gets stuck, so you will get afraid that don't know where it got stuck, maybe some ghost or something. So it's not like that some ghost is not making the block to move. There is some force only. So what force can come? Tell me. It's the friction force. And the friction force will always act in a manner such that it will try to oppose the relative motion between the surfaces. So suppose if I don't know why friction force acts, but still I can say there must be some force acting on the block, preventing the block from moving any further. And we see that acceleration of this block is 0. So in order to have net force 0, the force that must be acting backward must be of same magnitude as the applied force. The force that is going to act along the surface in the backward direction is going to be the friction force. And if I have the case when the block is at rest, so net force on it will be 0. And if net force is 0, then the force that we are applying on it must be same as the friction force or not. So when we don't see any slipping or any relative motion happening between the surface, so whatever friction force acts, that is whatever friction acts, it is called static friction, and name itself suggests static means not moving. Okay. So what I will do, I'll draw the graph between the friction force and the force that we are applying. So I write that point. Till no slipping or relative motion between surfaces, whatever friction force acts, just it is given a name, static friction. Okay. And the thing about static friction is it is kind of self-adjusting force. How? We'll see that also, or you may be knowing a little bit also, isn't it? Why self-adjusting? Suppose there's first of all that we can understand from common sense also, friction force can't be infinitely big, no? There will come a time when we apply a certain force, this block will start moving. So it means there is going to be an upper limit for the friction. Suppose the maximum friction force that it can apply is 10 newtons. In case if I am applying a force to move that block is 5 newtons, then the block will not move. So in that case, if I'll ask you what is the friction force, you will tell me, sir, it is 5 newtons. So getting the point. So it's like suppose if you have got 10 rupees in your bank account, and how much I can ask maximum from you? 10 only, no? If I'll ask you 5, you will give me 5 only. It's not like you will tell me, sir, you're a nice person, I'll give you 5 rupees extra. Correct. So whatever I'm asking you, that much only you will give me. So that's the same kind of thing here also. The friction, a maximum, suppose it can oppose is 10 and we are applying a force 5, it will be 5. When we apply a force 6 newtons, it will be 6. So depending upon what we are going to apply on the block, depending upon that, friction force will adjust itself to oppose any change in the, or oppose any kind of relative motion. Correct. That's why it is called self-adjusting force. So till the point we have got this block not moving, what we can say, the applied force F, capital F, is going to be same as the friction force, which we are using the symbol lowercase f or small f, no? So what I'll do is we'll keep the capital F on the horizontal axis. Any reason to keep the capital F on the horizontal axis? Anyone? Aswin, can you tell me? Why suppose if I am going to plot something, there's a reason why we keep anything on any axis. Just like that, because we like capital F. No, not like that. Suppose this thing is done in some manner such that we are applying a force F, but the block is resting on some rough vertical wall. Then how come you can think like that reason, man? That reason I thought no one will tell. I remember in basic maths class I told you what we draw on horizontal axis, because there's a question based on that in one chapter. Easy only. JEE means no. It is variant. I'm applying variable forces. It's not like force F is always constant. We are changing it. Yes, that is more correct. That is what I told you, that independent variable is drawn on horizontal axis. So depending upon what force F we apply, depending upon that, friction force will change itself. So who is independent in them among these two guys? The force that we are applying, no? Just like you can see, think like capital F is the input here and small f is the output. That is what Rupesh told, correct? See, he's listening things from the early class properly also. Because of that, he is able to tell. So what we have is, so when I have this capital F0, then what will be the friction force? Even if surface is rough, but if there is no slipping tendency, or if there is no slipping, then friction force will be 0. Friction force will come into picture only when there will be some tendency for the surfaces, or there is some tendency for the surface to slip onto each other. Otherwise it will not come. So when we have, so I'll write that point even. If capital F is 0, the friction force is going to be 0. Means friction will act only when there is any slipping happening, slipping is present, or tendency to slip is also there, no? Now what we find is that as long as the block is not going to slip, the applied force and friction force will be equal. Then what kind of graph we will get? Capital F equals to small f. So think like that, small f y, capital F x. So it is a graph of y equals to x. What is that? Identity function or not? Correct. So it is going to be, what is the straight line will be making from horizontal? 45 degrees now. So till the block is not going to move, the capital F will be small f. Till that point, whatever friction force acts, it is called static friction. Because it is independent variable, not constant. Independent, no? What input I give, depending upon that, output changes. So who depends upon what? Output depends upon input, no? So depending upon, suppose maximum friction force that can come into picture is 10. I apply 2. Then how much friction force is 2? Then I apply 5. Friction force is 5. So who decides what friction force will become? It is the applied force or not? What applied force will, so who is the independent? You can see that thing on your own. So what we find, and you must have seen that thing on your own also, that whenever you're trying to push some heavy table or block, then you will find in the beginning it will be like totally difficult to move that thing. But once the sleeping starts, you will find the effort that you need to apply to keep that block continue moving will be very much less than the one that you applied to make it to start move. No? Is it not? So what happens, as you suppose the maximum friction force can act is 10, and then I apply 2, friction force will be 2. I apply 5, friction force will be 5. I apply 8, friction force will be 8. I apply 9, friction force will be 9. I apply 10, friction force will be 10. But the moment I apply 10, no, it will, the moment I apply a little bit more than 10, maybe 10.001, automatically you will find the friction force will reduce by very small amount, and it will become little bit less than 10. And then afterwards, it will remain equal to that. Maybe for an example, the moment you apply 10.0001 Newton, the friction force will reduce slightly, and maybe it will become 9.8 Newton. And from that point onwards, it doesn't matter what force you apply, as long as it is bigger than the maximum friction can manage, the friction force will remain constant 9.8 forever. So what we find is that the graph will keep on increasing. There will come a time when that time will come when the sleeping will start, or on the verge of sleeping. There the friction force becomes maximum, and the moment we apply anything little bit more than that, it will reduce by small amount. That region I'll draw with the yellow color. And just a second. And from that point onwards, the friction force remains uniform and constant. So this is the point when the sleeping starts. Please tell me. No. Static. No. It doesn't depend upon force only. But if there is no sleeping, then friction force will come. No. Correct. And suppose maximum. So suppose if you have 10 rupees in your account and you're totally good guy, you can give any amount of money to anyone asking from you. So how much money you will give will depend upon the amount asked from you or not. This doesn't mean that anyone will ask 1 rupee, always you will give 10 rupees. It's not going to happen, no? Same thing here. So obviously the money, whatever will be in your account, doesn't depend upon what I'm asking from you. It will depend upon how much your father might have given to you, correct? But once you have that money, then how much you are going to give it to me, that will depend upon how much money you have in your account, and as well as how much I'm asking from you. Now you got the difference and similarity both. Okay. So the moment we apply a force a bit more than what friction maximum can manage, the friction force reduces a little bit. That is the point when the slipping starts. And from that point onwards, the friction remains constant, and it will be equal to that reduced value. And the reduction is not much. Maybe maximum friction can handle is 10. So the moment you apply anything more than 10, it will become 9. Not much difference. So once the slipping starts, or if there is any relative motion, then whatever friction force is going to act is going to be constant, and it is given a name, kinetic friction, name itself. No, kinetic means motion, moving, something like that, not kinetic Honda. But no. So this is the zone when friction will be called as kinetic friction, when it is going to happen when slipping is present. And this is the point when slipping starts. And what is the maximum the friction can provide? This is that. No? And that I'll write down as F max. But there's a name given to it called limiting friction. A name itself correct. No? You get that why it is called limiting friction? It is the maximum it can apply. Okay, no. And then the moment we apply any force more than F max, then friction force reduces a little bit and it remains constant after that. And that is called kinetic friction, and suppose I'll write it down as Fk. And this F max is going to be more than or equal to in general I'm writing it down fk. I write down more than fk, but it is the difference between them is not much. So if nothing mentioned, both we will consider same. If mentioned, then why we will consider same. If not mentioned, then we will consider both are same. I hope till here all of you understood now. Okay. See, I'll tell you. Suppose if I give you that maximum friction force that can come is 10, and the moment I apply more than 10.10, more than 10, maybe 10.1, the friction force will reduce and will remain constant. Suppose it reduces to 9.8, and then after that you apply 11 Newton, 30 Newton, whatever, friction force will remain 9.8 only. So that 9.8 value is Fk. Got it? Understood now? After that, once sleeping is there, then friction force will remain constant. Then it will remain 9.8 afterwards for every force, as long as force is more than 10. Okay. There's a theory also. There's some by which we can explain this region. I'll tell you in the next slide. You copy this thing first. Just tell me. Just tell me. Because suddenly friction force drops, no? The moment you apply a little bit more than that, how much more than that? Anything more than that? 100 zeros. Didn't get you. No, 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 no. Why? Why? It suddenly drops. No, suddenly drops. It drops in some time, then it will, or over some force you increase it. In then it is there. Then there will be a straight line having some slope. But suddenly drop means what? There will be no change in x. Still there is change in y. Correct? What I told you, 10.00000 100 zeros you put and 1 you put. Even if you have force more than a little bit also, suddenly it will become less than 10. Now get that? Okay. Simple thing only or not. Put any extra theory, any big things not there. No simple common sense or not? Is it not? And as physics will progress, you will see it is easy only. Till rigid body dynamics, it may feel difficult but very interesting. That is guaranteed. After that, it is very easy because after that, no new thing we do. Same thing, different manner. And whatever new thing we do, that is no also very easy. After 9 8 9 years, what happens? Only thing that will keep your job interesting is student getting good college. Same thing teaching every year becomes boring also. So only job satisfaction I have is like you getting good college. Then I feel like that your money was justified and time which is more important. Copy or document tell me. Yes, from Sunday only. Sunday class is there. Sunday, nothing new I will teach you. We will do only questions in the class. For that reason, I've kept this extra class. Because Sunday, if I'll teach you, then Wednesday, you can't get good marks in physics. It's not chemistry, math that you, once you know, then day after tomorrow only you can sit and write the exam. Perfect thing is 1 month time after every topic. Then you become mature to do any kind of question on your own. Video on, video on. Yeah. Okay, I can take a new page now. A few points I'll tell that you should know. Friction force acts only when there is relative motion or at least the tendency to slip. Next, friction force. See, when I told you, one thing was common normal, other was common tangent. Friction force acts along common tangent direction in a manner to stop or try to stop the relative motion between the surfaces that are in contact, in a manner to stop or try to stop the relative motion between the surfaces that are in contact. And maybe just for the making you recall what was our common tangent and common normal. In general, what we do, we consider in general, no? We take two objects. If I take, in general, I can take both these objects to be having flat surface. That is not very general thing. General thing is both the surfaces that are in contact will be curved surface. So whatever surfaces that are in contact, at the point of contact, you drop a normal and then you drop a tangent. So the tangent dropped at the point of contact is called common tangent, and the other one is our common normal. Okay. Copy these 2 points. You said me. Friction force acts along common tangent in a manner to stop or try to stop the relative motion between the surfaces. That is something point I was going to explain that. I'll tell you now only. So if these two surfaces, the one that we have seen just now, a block kept on a flat rough surface, if it is being pulled, this block is being pulled in the rightward direction, then you see, if I'll ask why slipping happens, the reason why slipping is happening, this block is moving towards rightward direction, or you think that in case if friction was not there, how the surface of the block will move towards rightward. So to stop it from moving rightward, what way I must apply the force of friction? Back. Leftward, no, correct, no. So why we applied that? To prevent slipping, no. That's what, no. That is the second point, is no. Understood, no. So friction force on the block is acting backward, and on the surface will be acting forward, no. Action reaction pair. Okay. Okay. So the surface of the block, I can say this surface leads, means moves forward. So to stop it from leading, it must be dragged backward. And other way also I can say, no, like glass half full, half empty kind of thing. The reason why the slipping is happening because the ground is not moving along with the block. Suppose somehow if I can make the ground also to move along with the block as the block moves, then there will be no slipping, then there will be no requirement for the friction to come. So I can make the surfaces not to slip by making or by trying to make the ground to move along with the block, correct? So how friction force must act on the surface, must be forward or not? Getting the point? So the ground here is, I can say it is the lagging surface. So lagging surface must be made to lead so as to decrease the gap between the one that lags and the one that leads. Understood? No, lagging surface and leading surface. Just I made up this points on my own, but you get that what I mean by leading surface and the lagging surface. So lagging surface will try to make it not to lag behind. Yeah, why leading? Because it is the one that moves forward. Ground stays. Yeah, correct. Yeah, and other way, no, like why this glass is half empty. So I'll say the reason why slipping is happening because ground is not able to move with the block. Correct. That's why. How come? In case if it was possible, then how what I must do to make the ground to move along with the block? I must apply force onto it, which must make it to move along with the block in the rightward direction. So what force it must be in rightward direction? That friction force, and it will be in rightward direction. Understood? No? Okay. That was going to be explained in upcoming things when we do 2 block, 3 block problem. Maybe I don't know whether today we can do that or not. Next class we will be able to reach till there. So your syllabus will get over before only. Sunday we will do practice questions. Those who have missed classes, God help them. I told not to miss classes, the one I'm taking. Never. That I tell every year. Every year some percentage students will not follow. And those will pay 30 lakhs, 40 lakhs for BTech, which is total waste of money for doing BTech from such college by paying that huge amount. I will not do anything like that. So, so that will be there in weekend batch every time. You must accept that, okay? No? Because until unless we don't accept the reality, we can't do whatever is necessary to be done. Correct? Weekend batch, it will be like that, and phase 5 more mm, difficulty like that. I can, if you want, I can finish also. I'm telling you, but that is not something any teacher must do. But that is done all the places. How come anyone can finish on time? You can see the content or not. If anyone, if it is possible, if they live near, if feasible, must join weekday patches. It will be more better for you. Parmeshwar today here or not? Parmeshwar here, no? Not here. Okay, I can take a new page now. Now, the theory is like that, and that is true also. So what we say is that suppose if I look to surface very closely, it's not going to be a very even surface. It will have unevenness at the atomic level. So the two surfaces that are in contact will have uneven surfaces having valleys and troughs like that, or ridges like that, and because of which there will be some interlocking happening between the surfaces. Now, suppose if I try to pull the upper surface by lot of force, in that case, I may manage to make the surfaces to be more smoother. No? Suppose if you grind your teeth a lot, your teeth will become more blunt or not, or it will become less sharper or not. Correct? It's the same sort of thing we can say, it's like simple common sense kind of theory. So when we apply enough amount of force, then maybe I can break some of the valleys here and I can make things more smoother. That's why once slipping starts, the friction force reduces by some small amount. Get that point? Why it is like that? Earlier the locking was more, then I apply some force that I can break some of the locking in there and make the surfaces becomes little bit more smoother, more like a little bit more smoother, like so they rub the marble no to make it more shinier and more smoother no. So rubbing we can make things smoother or not. So there we are trying to rub one surface over other, so we may break some of the valleys, ridges, and interlocking becomes less effective, because of which friction force reduces by some small amount. So that is the reason we, and that is totally feels logical also no, that why the kinetic friction is going to be lesser than the maximum friction can oppose. Now, suppose if I'll keep two surfaces more pressed into each other, correct? In that case, what will happen? The interlocking will become more effective or not? Is it not? So we can say the more the surfaces are pressed into each other, suppose if I press my two hands more with more force towards each other, in that case it will become more difficult to have that relative motion or not. So I can say that friction force is going to be directly proportional to the normal contact force, the one that we have acting between the surfaces that are in contact. Why? Because more normal contact force we have, the more interlocking will be there. Is it not? Yeah, no, not more interlocking. More interlocking will become more effective or not. That's why the friction force, thus we will talk about the static friction. So we have seen and understood the point that why it is called self-adjusting force. The static friction is going to lie between whatever the maximum friction can oppose and zero, no? Because in the case when I'm not having any relative motion, friction force will be zero. But in case if I have, if I try to have some, friction force will come into picture and will oppose up to a certain limit the maximum friction force, whatever it can be, called limiting friction also. So experimentally and by common sense also we see that this maximum friction force called limiting friction is going to be directly proportional to the normal contact force between the surfaces that are in contact. And to get rid of this proportionality sign, we bring a proportionality constant. So that will be, so this is mu s, I'll bring that coefficient of that we bring that constant, this mu s, which is called the coefficient of static friction. Now suppose if I have two surfaces which are oiled, or maybe some lubricant is placed between two surfaces, in that case even if you have normal contact force more, but still friction force will not be much more as compared to the one that is not lubricated. So it's not, so friction force is not just going to depend upon the normal contact force, it will also depend upon what kind of surfaces or the properties of the surfaces that are in contact. Is it not? That's why that mu s is going to take care of that particular thing. So coefficient of static friction is going to be depending upon the surfaces that are in contact. So our static friction is going to lie between 0 to a maximum value, which is going to be mu s times n. Next we will talk about kinetic friction. Just like static friction, the kinetic friction is also going to be directly proportional to the normal contact force. To get rid of that mu k, yeah. So this is called coefficient of kinetic friction, and that too depends upon the surfaces that are in contact. And in general, mu s is going to be more than mu k if nothing mentioned. What you will do, you will consider them to be nearly equal, and in reality they are not much different also. If one is 19, other will be 20, that much difference in general. So I hope all of you understood this up till here. Easy only. Very not delta. One is suppose 0. The other maybe 0.23. Difference is not huge. That is I'm trying to tell. Less only. How much difference? Then again, it will depend upon what kind of surfaces we are talking about. If it is easier to make the surfaces smoother by, tell me, the friction force should depend upon the area of the contact or not. Maybe I'll take something. Suppose if I'll keep my mobile like this, and then I drag. You can see that in just a moment. Video is on only. Yeah. I'll keep my mobile like this and drag it on a surface. Then I keep it flat like that, and then I drag it on a surface. Friction force will be same or different. When it is in this case lying in contact like that, it is going to be less or more. Tell me. In this case or this case? Why? So what I'm trying to, why I ask this question is, don't put any ideas whichever you feel intuitive. Okay. Did I told anything like that? No. But I told friction force directly proportional to normal contact force, and it depends upon mu s mu k. But does that area thing anywhere mentioned? No. Did I mention that? No. So it doesn't depend upon area. So you must be stickler to the rules. If you are, then you will become good in physics also. That's why in Sanskrit, physics is given a name. Nyaya Shastra means, Nyaya means like rules and all. Shastra means science. Rules of science. A science of rules. And it is not wrong name also, no? So I did not mention the area. Why you think something on your own? Don't understood, no? Doesn't depend upon area of contact. Depends upon only the normal contact force. Then it doesn't feel intuitive, no? But it is. How? If I have kept this block like that, or if I keep the block like this, in either case, the normal contact force will be same or different. Tell me. Same, no? If you have copied, I'll take a new page. Maybe I'll draw the figure here also. Suppose if I keep a surface like this, a block like this, same block of mass m, then I keep the same block like this. In either case, the normal contact force will be same or not? Same, no? All of you can look and tell, no? And upward mg down. So normal contact force same. So what we have is the same normal contact force in this case 1 is acting over an area which is bigger. In case 2, same amount of force is acting over an area which is smaller. So in case 1, we have got more area in contact, so we have got more number of interlocking. But there, the force is applied over a smaller area, bigger area, so pressure is less. So the each interlockings are going to be less effective than case 2. In case 2, we have less number of interlocking because less area in contact, but the normal contact force per unit area is bigger. So the interlockings will become more effective than case 1. So overall effect happens to be that friction force comes out to be same. Understanding this point? Getting the point or not? say one time, suppose elephant will keep his leg on your leg, and maybe someone wearing heels and will keep his leg on your leg. That I learned that thing in 5th class. My teacher told me pressure will be more in which case? In the case of heel one, because force is less, but the area over which force we are applying is very very small. So maybe elephant may not be doing that much damage to the skin, but that you can make a hole, or you can puncture, or you can fail the material of a paper by using a needle easily than using some blunt thing, no? Because you apply a force on a smaller area using a needle, because of which the pressure is going to be more, because of which the material fails more easier. So case 2, I have got pressure more, so each locking becomes more effective even if there is less number of interlocking, because there is lesser area that are in contact. I hope all of you understood that. Okay, now copy this thing. After copying, tell me. I can take a new page now. Maybe you might be knowing in this all also a little bit. Okay, then I'll take a new page in case if you're not copied, you tell me. There's something called angle of friction. What is that? In lab, experimentally, how we figure out. Okay, no problem. Just tell me. Didn't get you. One directional. It can no any kind of motion. If slipping is there and the surfaces are rough, friction force will come. Okay, no? But it will come in a manner to prevent slipping, depending upon how the surfaces are trying to slip over one another. Every vector can have any components. Every vector can have any components. Is it? So friction force does not depend upon area of contact if pressure is not extremely or extremely high.